All right, let's get into it. So, you've built an autoencoder, but how do you make it, good? It's not just about the architecture. The real magic is in the tuning. We're going to talk about the key parameters that control how it learns, making sure it actually understands your data instead of just, becoming a super complicated copy-paste machine.
So what are we actually tweaking here? I like to think of hyperparameters as the dials and knobs you get to turn to control how this thing learns. Because, let's be honest, if it just perfectly copies the input, what's the point? It's learned nothing. Our goal is to tune these knobs just right so it's forced to learn the essence of the data, not just the surface-level details.
Okay, first up, and you could argue this is the most important knob of all, the loss function. This is basically the autoencoder's report card. It's how we measure its success and tell it, hey, you're doing a good job, or nope, try again.
So what is it really? It's just a function that looks at the original input and the reconstructed output and calculates the difference, the error. And the entire game during training is to get that error number as close to zero as humanly or machinely possible. Minimize that loss, that's the whole point.
A super common choice, especially if you're working with something like image data, is mean squared error, or MSE. It's pretty much what it sounds like. It calculates the average squared difference between the original pixel and the new one. It's a fantastic starting point, kind of like the factory default setting for your loss function.
But what if just copying isn't enough? What if we want it to learn something deeper? Well, this is where things get really interesting. We can actually start messing with the loss function to make it do more than just reconstruct.
Take a look at this. This is for something called a sparse autoencoder. We actually add a penalty to our loss function. See that little omega symbol? That's our penalty. It basically punishes the model for using too many of its brain cells, its neurons, at the same time. We're telling it, look, I still want you to reconstruct the input, but you have to do it using as few resources as possible. This forces it to find the absolute most important features and ignore the rest.
Now, here's another really cool trick, denoising autoencoders. Instead of adding a penalty, we change the whole goal. We intentionally break the input. Imagine feeding it a photo, but with a bunch of random static added on top. Then, you tell the autoencoder, your job is to give me back the original, clean photo. By doing this over and over, it gets amazing at figuring out what's the important stuff, the signal, and what's just junk, the noise.
All right, let's turn to our next style, activation functions. So if the loss function sets the overall goal for the network, the activation function is like the rule each individual neuron has to follow. It decides whether a neuron fires and what signal it passes on. This is what lets the network learn all those cool, complex patterns.
So, the sources we looked at point to two really common ones. First, there's ReLU, which stands for Rectified Linear Unit. This one is a big deal for those sparse autoencoders we were just talking about. Then you've got softmax. This one's your go-to for the very last layer when you're trying to classify things into different buckets or categories.
And here's why ReLU is so special for sparsity. Look at the graph. If the input is negative, the output is just zero, a hard zero. This is huge. It means a neuron can be completely switched off. This is exactly what we need to achieve that sparsity we were talking about before. It gives the network the ability to say, nope, this feature isn't important, and just shut that neuron down, forcing it to be efficient.
So, we've hit two of the big ones, loss functions and activation functions. Now, I want to be super clear about the scope of this particular explainer. We're sticking strictly to what our source material covered. And that means that while we got a really good look at loss and activation functions, things like learning rate, batch size, early stopping, or initialization weren't discussed in the material we pulled from. So for today, we're keeping our focus right on the stuff we could confirm. Which really brings us back to the big central question of it all. If your autoencoder just becomes a perfect copy machine, has it learned anything? Anything useful at all? The answer, of course, is a big no. And that is exactly why getting a feel for these dials and knobs, these hyperparameters, isn't just a detail, it's the entire point of building a great autoencoder in the first place.